computer. So you have sketch the solids. Sketch the solids whose volume is given by, okay, and now problem A, the triple integral r dz dr d theta. Obviously, the integral is given in cylindrical coordinates. Okay, theta goes from 0 to pi. R goes from 0 to -3 cosine of theta. So as you can see, it's a little bit tricky. So we need to solve it quite a bit. We've never seen an example like this where R goes from 0 to negative cosine of 3, and then Z goes from 0 to R. It is always helpful to write this down, to write the bounds, right? So first of all, the easiest one, theta is between 0 and pi. Then the next one is what? It's R, right? So R goes from 0 to -3 cosine of theta. And at the end, Z. Z is between 0 and R. Okay. So let us first look at these two, right? So R is equal to -3 cosine of theta. What is represented by this graph, right? So we are going by this curve. We're going in 2 dimensions right now. Okay, so I have X and Y, and here I have, first of all, I can write here theta and R, right? So when R is 0, sorry, when theta is 0, R is -3, 1, 2, 3, and then I have 1, 2, 3, 4. This is pi over 2, and this is pi. Okay. When theta is going from 0 towards pi over 2, right? This is becoming smaller and smaller, right? So it goes towards 0. So it's like this. Then 1, 2, 3. This is -3, right? And here I stop because theta goes from 0 to pi. Okay. So then what is this? What is represented by this curve, right, in the xy plane? Well, look at this. When theta opens from 0 to pi over 2, the radius is negative. So in this quadrant, when theta opens from 0 to pi over 2, right, the radius is going to pop out in the third quadrant, right? We learned that when R is defined as -3 cosine theta, for all the positive values of cosine, and those happen in the first quadrant, the radius is negative. That means it's going to show in the third quadrant, right? So we start at 0. Sorry, my bad. We start at -3. So when theta is 0, R is -3. So 1, 2, 3. Theta is 0, right? R is -3. Okay. And then as the angle goes towards pi over 2, right? The radius diminishes, right? Becomes smaller and smaller and reaches zero at pi over 2. Then from pi over 2 to pi, the radius is positive from pi over 2 to pi. So in this quadrant, the radius is positive. So that means it's going to show up in the same quadrant, right? So we go from 0, the radius goes from 0 to 3. So basically, this is nothing else but a circle, right? Okay, how are we going to represent this in 3 dimensions? So in 3 dimensions, y and here x, okay? So obviously this circle is on the negative side of the x-axis. So basically this circle is right here. Okay. And at the end, I have to figure out what happens to z. Well, z starts from 0, right? And it's less than, what is r in Cartesian coordinates? Well, r is just the square root of x squared plus y squared. Okay, so z, this means that z is bounded above by the solid represented by square root of x squared plus y squared. Well, what is this? Who is going to tell me? We keep on seeing this over and over. What is this?
Isn't that a cone?
It's a cone, right? So basically, what do we have here? I have, for if I have only this circle here, for any given z greater than 0, I'll have a cylinder, right? And then I intercept that cylinder with this cone, only positive, right? So what is going to be the intersection? The intersection is going to look like this. And this should be a real straight line. So that's the solid represented by this triple integral. Any questions? No questions? Well, because this is not, be careful, the cone here is not, the cone here is not a plane, so this is not going to be the ceiling here is not going to be a plane like boundary, right? It's going to be dented a little bit. It goes like this a little bit on the in the upper limit, right? It's like scooped a little bit, but I don't know how to sketch that because this is the cone, right? The cone goes like this, so it just basically it scoops this a little bit. Let's say I don't know how else to represent that. Any questions? Okay. Maybe the same problem too. So this is nothing else but basically recognizing what solid are we talking about given these boundaries, right? Something that we have in a way been doing a few months ago, right? When we talked about cylindrical and polar and spherical coordinates. Okay, so the same question, sketch the solid represented by whose volume is represented by the following triple interval. So this is rho squared sine of phi d rho d phi, yay, d theta. You can have. I'm working, sweetie. You have to go. Pi over 4 to pi over 2, and then 0 to 2 times cosine of phi. Okay. So let's write down the bounds, right? Theta does a full circle from 0 to 2 pi. Phi just goes from pi over 4 to pi over 2, and then rho goes from 0 to 2 times cosine of phi. So rho is not a constant, okay? Well, this means that we are making the solid is making a full circle around the z-axis. That's fine, no problems there. This means that phi means that in 3 dimensions, we're just going to start at pi over 4, and then we're just going to go to pi over 2. And then when you spin this around the x-axis, sorry, the z-axis, you're going to get something like that, right? That would be for any given rho. And now the question here is just what happens to rho, right? So basically, I want to know, what does this look like? Okay, what kind of solid is represented by this? Well, how to do this? I know what rho squared stands for, right? Rho squared is equal to x squared plus y squared plus z squared. I told you, you should know those, right? So the first thing I want to do is multiply this equation by rho, and I get rho squared is equal to 2 times rho cosine of phi. Now, as I said, this is x squared plus y squared plus z squared is equal to 2 times this in spherical coordinates is nothing else but the z value. Z is equal to rho cosine phi. And now, I don't know if you already recognize this or not, right? Because I've done quite a lot of these problems. I can see that this is going to be a sphere centered at, not at the origin, but somewhere is going to be adjusted on the z-axis, okay? So what do we have to do? We have to complete the square, x squared plus y squared plus z squared minus 2z is equal to 0, right? I brought 2z on this side. How do I complete this square right here? Well, I need to add 1. If I add 1 on the left-hand side, I need to add 1 on the right-hand side, and I have x squared plus y squared plus z minus 1 squared is equal to 1, which is a sphere centered at the point 0, 0, 1. Okay, always be careful here, right? I can play with this. On this side, it might pop out y or x. Okay, so that means that just the center is going to be moved back or forth with radius 1, one squared, right? Okay, so now we have everything. This is going to be a so this is the x-axis, the y-axis, and the z-axis, okay? So if this is 1, let's say this is 2, the center of the sphere is here. I guess my son stole my, how do you call this, compass in English, right? So, okay, so that's not gonna be very fancy, but I'm looking for fancy. This is the best circle that I can do, okay? And then, so this is going to be like this is a sphere, right? Okay. And then from pi over 4, let's say pi over 4 is here, from pi over 4 to pi over 2. So basically this is the solid that we are talking about. Tukaj je pod masa, Marko. Okay, so we concentrate on this solid here. If you can imagine it, rotated around the, so this like this. Right, I don't know how like this. Right. If you rotate this. So this is the outside wall of the solid, and in here it's empty, right? So that is the solid represented by, whose volume is represented by this triple integral. Any questions? Last question of this type, part C. This one is going to be the easiest one. Why? Well, you'll see in a second. Theta goes from 0 to 2 pi. Phi goes from pi over 2 to 2 pi over 3. And then rho goes from 0 to 2, right? Rho being a constant, what do we describe? We describe a circle a sphere, not a circle. We describe a sphere centered at the origin, okay? So this is here just the Jacobian, so don't get confused by it. So R is between 0 and 2, phi is between pi over 2, and this is the only interesting part about this question, because phi is basically below the z-axis, right? Below the xy plane, what I wanted to say, for negative values of z. 2 pi over 3, and theta is between 0 and 2 pi. Okay, so because, as I said, because phi goes from pi over 2 to 3 pi over 2, our solid is going to be below the xy plane. This is y, this is x, this is z. Let's just use this circle here that I already started to represent our sphere. Okay, and then only because we are talking about, so that means that theta spins a full circle, 360 degrees. So we're just talking about this, right? So I have and then this here is empty. And then these are what this goes around, right? So any questions? Of course, we have the walls like this. No questions? Okay, standard problem. Standard problem in triple integral is switching between spherical, cylindrical, and Cartesian coordinates. Okay, so write the given integral in A, Cartesian coordinates or rectangular coordinates. B, spherical coordinate. and C evaluated. Okay, the integral is from 0 to 2 pi d theta, from 0 to square root of 2 dr, and from r to square root of 4 minus r dz, 3r. Okay, obviously our integral, the given integral, is in cylindrical coordinates. Okay, this here is the Jacobian, right? So that will not affect, this is not the integrand. Okay. Okay, so what is the integrand? The integrand is the constant 3. If this was here some other function defined in either theta or z or r, you should appropriately change that to rectangular or spherical coordinates. Okay, so let's do the this problem. Part A. Switch this to rectangular coordinates. Here I'm going to write the bounds. Theta is between 0 and 2 pi, r is between 0 and square root of 2, and z is between r and square root of 4 minus r. Okay? By sketching this situation, right? By sketching this situation, my answers are going to be in front of me. Okay? So the only, basically the moment I'm gonna flip this into Cartesian coordinates in order to sketch it, I'll basically have the bounds for z. Okay, so let's first see what is z is equal to r. How does that look? Well, r in rectangular coordinates, r squared is x squared plus y squared, which means r is square root of x squared plus y squared, right? So I get from here that square root of x squared plus y squared is the lower bound of z. And then you have z being equal to square root of 4 minus r squared is nothing else but 4 minus x squared minus y squared. 4 minus x squared minus y squared. Okay?
Ivo, this might be a mistake when you wrote the question, but it's written like 4 minus
4 minus r squared. 4 minus r squared. Sorry? 4 minus r squared. My bad.
No, that makes more sense, yeah.
You're right. Thanks a lot. Okay, so let's catch these two situations. Okay, so first of all, this here, z is equal to square root of x squared plus y squared is a cone. Okay, this here is a sphere. If you need an explanation on that, about the sphere, z is equal to hemisphere. Hemisphere because it's positive square root. Okay, so 4 minus x squared minus y squared, square both sides, z squared is equal to 4 minus x squared minus y squared. Bring x and y on the other side, x squared plus y squared plus z squared is equal to 4, which is 2 squared. So is a circle centered at the origin with radius 2. The fact that I have only positive square root here, right? It means that we are talking about a semicircle. So 1, 2, 1, 2. And then 1, 2. So this semicircle. Hemisphere, sorry. And then I have the cone. Okay, so Z is above the cone and below the hemisphere. Okay, so basically the solid that we are talking about is this one, and then we've worked with this one over and over again, right? And it should not be a problem for you. So only this part right here. Okay. So how do I switch from here? How do I go back into rectangular coordinates? Well, first of all, I have already the bound on Z. The bound on Z is, we've already done it, right? It's right here. Now, how do we find the bounds on X and Y? In order to do that, you have to look at the shade, right, that this solid has on the XY plane, or simply the projection of the intersection of the cone and the hemisphere onto the XY plane. So let us find the intersection between the cone and the hemisphere. How to do that? Well, all you have to do is put these two together, right, and solve for get rid of the square root, basically. So you have square root of x squared plus y squared is equal to square root of 4 minus x squared minus y squared, right? So I'm putting these two together equal to each other. That's when the z value is the same in this disk, this circle. Square both sides, z squared plus y squared is equal to 4 minus x squared minus y squared minus, right? Well, let's put it plus because, but with parentheses here. Bring this on this side, you get 2x squared plus y squared is equal to 4. Or that's x squared plus y squared is equal to 2, which means in the xy plane, we're talking about a circle with radius square root of 2. So in the xy plane, we're talking about a circle with a radius square root of 2. And now it's up to you how you're going to write down this in rectangular coordinates. So basically, I'm just writing the question here from 0 to 2 pi, from 0 to square root of 2, and from r to square root of 4 minus r squared, 3r dz dr d theta is equal to, this was the Jacobian, right? So the integrand is just going to be 3, right? And then choose dz. I already have z expressed in terms of x and y, so that's why I'm going to integrate first with respect to z, okay? And then based on your choice, that's how you're going to find the bounds on x and y. So let's say dx dy. Okay, so dz, as we have seen, is going from square root of x squared plus y squared, and the ceiling is the hemisphere, 4 minus x squared minus y squared. Now x has to be expressed in terms of y. This here is x squared plus y squared is equal to 2. So that means that x squared is equal to 2 minus y squared, which means that x is less than square root of 2 minus y squared, but it's greater than negative square root of 2 minus y squared. So from negative square root of 2 minus y squared to square root of 2 minus y squared. And finally, y, well, y goes from negative square root of 2 to square root of 2. This is the answer to part A, when I have expressed this in terms of rectangular coordinates. Any questions? Okay, if there are no questions, I go back to the sketch here and I'm trying to figure out how to express this in spherical coordinates. Okay, so spherical coordinates is rho squared sine phi d rho d phi d theta. Okay, and from here all I know is that theta goes from 0 to 2 pi, which is the same as the one that was given at the very beginning, right? So I have theta between 0 and 2 pi. How I'm going to find rho and how I'm going to find phi? Well, I'm going to find rho from the sphere, right? Because as you can see here, the upper limit on rho is constant. It goes from 0 to the hemisphere, and then it's the same here, right? So I can fall. So I don't even have to evaluate anything. I will do it. I will do it just for you, but I don't have to bother with it because if your sketch is correct, then you're done. So I already know that rho is going to be between 0 and 2, and I will obtain that, if not from the sketch, then from just the equation of the sphere right here. So the hemisphere, z is equal to square root of 4 minus x squared minus y squared. Okay, let's turn this into spherical coordinates. Rho cosine phi is equal to square root of 4 minus x squared plus y squared. And I told you to know x squared plus y squared and x squared plus y squared plus z squared in spherical coordinates. X squared plus y squared is rho squared sine squared phi. And if you don't know it, it's also fine. You can simply evaluate this. So this is equal to 4 minus rho squared times sine squared phi. Okay, square both sides, you get rho squared cosine squared phi is equal to 4 minus rho squared sine squared phi. Bring this on this side, you get rho squared cosine squared phi plus rho squared sine squared phi being equal to 4. Factor rho squared here, you get cosine squared phi plus sine squared phi is equal to 4. This is 1, so rho squared is equal to 4. And rho is positive, which means that only rho is equal to 2, right? So the upper limit of the radius is 2. Okay? And then phi, well, phi, look at the picture, like how am I going to get how much is this angle? This angle right here. Well, that's given by the cone. Okay? So look at the cone. And the cone was given by z is equal to square root of x squared plus y squared. Okay, any questions? So let's look at the cone. So z is equal to square root of x squared plus y squared. This x squared plus y squared shows again that's rho squared sine squared phi. On this side I have rho cosine phi. Rho cosine phi is equal to square root of rho is rho, square root of sine squared is sine phi. Cancel rho and rho. At what angle? at what angle between 0 and pi? Between 0 and pi, cosine phi and sine phi are the same. Phi is equal to pi over 4. Okay, so why don't you guys write down this triple integral while I chat with my son if he can play piano while I'm teaching or not. Give me a second. Okay, sorry about that. So phi goes from 0 to pi over 4, and then the triple integral is from 0 to 2 pi d theta from 0 to pi over 4 d phi, and then what did we say? The rho, I lost that. Rho goes from 0 to 2. Rho goes from 0 to 2. The rho, okay? The integrand is 3. And then don't forget the Jacobian, okay? Very important. The Jacobian in spherical coordinates is rho squared sine of phi. Any questions? And then in part C, we have to evaluate how much is this integral, and you have to decide what would be the best option, the easiest option. So I'm evaluating integrals without thinking whether this square root is gonna come out nice. It has square roots. We're talking about integrals. I just decided to run away from it, right? Similarly here in Cartesian coordinates, even worse, right? So the spherical coordinates look like the best option. So I'm just going to continue. This is going to be very, very simple integral, especially because in spherical coordinates, none of the values depend among each other. So right away I can write this is the integrand is expressed as a product of independent functions. So integral of theta, integral of d theta is just theta evaluated from 0 to 2 pi times integral of phi, integral of sine of phi is negative cosine of phi evaluated from 0 to pi over 4, and the integral of rho squared is 1/3 rho cubed evaluated from 0 to 2. Don't forget the constant at the beginning, 3, and then I don't know, this is 3 times 2 pi times negative cosine of pi over 4 is square root of 2 over 2 minus cosine of 0 is 1 times 1/3. 2 cubed is 8 minus 0. These guys are out. So this is 8 times 2 is 16 pi, right? 8 times 2 is 16 pi times 1 minus square root of 2 over 2. And then if you want to take it one more extra step, 8 pi times 2 minus square root of 2. Any questions? And I have only 2 more questions for today, for this semester. As a matter of fact, both of them are involving finding the volume of a solid. So problem 3. Find the volume of the solid bounded below by the paraboloid z is equal to x squared plus y squared, laterally by y, by the cylinder x squared plus y squared is equal to 1. And this is a good enough hint Okay, how are we going to proceed in this problem? And above, by the paraboloid x squared plus y squared plus 1 is equal to z. So let's look at the how this solid actually looks like. Okay, first of all, I have the paraboloid x squared plus y squared is equal to z. Right, so this is z is equal to x squared plus y squared. Then I have the cylinder x squared plus y squared is equal to 1. So this is the floor, right? Because it says bounded below by this paraboloid, which means that my solid starts from this paraboloid going up, right? So the cylinder x squared plus y squared is equal to 1. Let's say this is negative 1 and 1. Okay, and at the end I have the paraboloid x squared plus y squared plus 1 is equal to z, which means it's this solid just shifted for 1 unit along the z-axis. Let's say this is 1. Okay, so basically, if this is the floor, sorry, the ceiling, and this is the floor, what do we actually obtain? Okay, so I obtain this. This is the upper part, so I can see the whole disk, right? Lateral is bounded by the cylinder. So this is the solid that I want to. So it's basically a cylinder that has indentation on top, and then it has this paraboloidal part, which I don't even know if it's a word, in the bottom. Okay, so the volume in cylindrical coordinates is this r times dv over the region E. We're gonna find these bounds very soon. Okay, so that's r dz dr d theta, where r and theta are being found from the projection of the solid onto the xy plane. Okay, so let's start one by one. First of all, z obviously is bounded between, where is it, x squared plus y squared and 1 plus x squared plus y squared. Well, in cylindrical coordinates, again, r is x squared plus y squared, sorry, r squared, right? So that means that in cylindrical coordinates, z is above r squared, below by 1 plus r squared. Okay, and now the bounds of r and theta, again, I'm going to say, are given by the shade that throws this solid onto the xy plane, but that is, in this simple case, that's given by the circle x squared plus y squared is equal to 1. So in the xy plane, x and y. This is the circle x squared plus y squared is equal to 1. And from here, obviously, theta goes from 0 to 2 pi, and r goes from 0 to 1. So finally, I can write this triple integral. Theta goes from 0 to 2 pi. R goes from 0 to 1. And z goes from r squared to 1 plus r squared. The integrand is r, the Jacobian, right? So this is equal to, if you have done enough examples or you plan to do enough examples, you'll get accustomed to this. Okay, I'm integrating theta. Theta is independent. Integral of d theta is just theta. Theta value from 0 to 2 pi is 2 pi. Okay, this comes from the integral of d theta from 0 to 2 pi times the integral from 0 to 1 times r, right? And first I evaluate this integral, dz, but that's just z evaluated from r squared to 1 plus r squared dr, and this is 2 pi integral from r 1 plus r squared minus r squared dr evaluated from 0 to 1. R squared and r squared cancels, so this is a very, very simple integral in cylindrical coordinates. Integral of r dr is just 1/2 r squared, evaluated from 0 to 1 is 1. Cancel 2 and 2, your answer is just pi. Any questions? No questions? And the final problem, like this live, right? As I said, I'm going to record one more session as a review of test number 4. But the last problem is going to be sketch the solid bounded by rho is equal to 1. Okay, so now I'm giving you the solid and spherical coordinates, right? Z and a little bit of Cartesian. Z is, so this is a mixed. Is anybody here Italian? Nobody has Italian origin? None of you?
Yes.
Who said yes? Melissa?
Melissa and Sonia.
Melissa, what do you, when you say Macedonia, what do you mean by that?
I don't know.
Really?
No, I don't know.
It's a fruit salad.
Okay.
It's a mixed fruit salad. Also the name of my country. I don't know how I feel about this, Melissa. I'm kidding.
Okay.
Nobody found that interesting? Okay, I'm just going to move on. Obviously, not the day to become a comedian. And above, by the cardioid, rho is equal to 1 plus cosine of phi. Okay, so it's a mix, like a salad, a little bit of spherical, a little bit of Cartesian, and so on and so on. Okay, so rho is equal to 1. That should be easy. It's a sphere, right? It's a sphere with radius 1. If you wonder if I could sketch the sphere a little bit smaller, yes, I can. The thing is, what happens to this guy here that we've never seen it before, right? It's a little bit off. It's a little bit, It's a little bit strange, okay? So how am I going to get a sense of it? Well, let's take theta to be equal to 0. Okay, so basically let us operate in the xy plane only. Okay, or theta to be equal to pi over 2, sorry. Right? So let's take theta is equal to pi over 2, so we'll just work in the yz plane. And then we'll spin this around the z-axis, and then we'll see what is going to happen, okay? So let's see what this looks like, although you should be able to recognize it if this is phi, and this is here rho, okay? So I have 1, 2, 3, 4, pi over 2, pi. What else? 3 pi over 2 and 2 pi, okay? And when theta is 0, cosine of 0 is 1, 1 plus 1 is 2, so 1, 2, okay? As I'm going towards pi over 2, this part here diminishes, becomes 0 at pi over 2, so rho at pi over 2 is just 1. When phi is pi, cosine of pi is negative 1, 1 minus 1 is 0. And then here, obviously, you can expect what's going to happen with the rest of this curve. Is just the cosine curve, right? So what do I get? I'll get the, as it says, cardioid, right? So when theta is 0, I get 1, 2. What did I do? No. I got some mistake here. So 2, then it's 1, then it's 0. So it's like this, right? And then like this. This is not y and. Okay, sorry. Now I get it. So now, because phi opens from here, right, from the positive z-axis, right, when phi is 0, right, rho is 2, so 1, 2 here. I start from here, and then phi opens up this way, right? As we are going towards pi over 2, right? As I go towards pi over 2, rho comes down to 1, right? So basically, this here is going to be the sphere in 3 dimensions. Why do I stop right here? Because of this bound here, z is always positive. Okay. So now, as we said, spin this for pi over 2. Okay. Spin theta around, and you'll get this shape right here. Okay, so this is 1 and negative 1. Okay. But on the other hand, that's the cardioid. On the other hand, I have rho is equal to 1, so I get this solid. Okay, so the solid is the interior of this that's represented here. Any questions? So here basically it's empty in here. Okay. And that's about it. Basically, rho is already given in terms of the bounds of rho are already given. So rho is between 1 and bounded above by 1 plus cosine of phi. Okay. Phi goes from 0 to pi over 2. And theta just goes around from 0 to 2 pi. And now write this, the volume is equal to the triple integral, right, from 0 to 2 pi d theta, from 0 to pi over 2 d phi, and from 1 to 1 plus cosine of phi d rho, right? Volume of 1 times the Jacobian is rho squared sine of phi. And this is an easy integral to evaluate. So that's theta evaluated from 0 to 2 pi. That's 1/3 rho. No, sorry. I skipped there because why? Because rho depends on phi. So times the integral from 0 to pi over 2. Integral of rho squared d rho is 1 over 3 rho cubed, evaluated from 1 to 1 plus cosine of phi. D phi. Okay, so this is 2 pi times the integral of 0 to pi over 2. Well, 2 pi over 3 actually. I pulled this constant out. And then here, I forgot sine of phi. And here I have 1 plus cosine of phi cubed minus 1, right, when I evaluate this antiderivative at the endpoints, times sine of phi d phi. Okay. So here, this is equal to 2 pi over 3, integral from 0 to pi over 2. The binomial formula, 1 plus 2 times 1 cubed times cosine phi, plus 2 times 1 times cosine cubed, cosine squared phi, plus cosine cubed phi, minus 1 sine of phi d phi, which is equal to 2 pi over 3 times the integral of 0 to pi over 2. And then I have 2 times cosine of phi plus 2 times cosine squared of phi plus cosine cubed of phi times sine of phi d phi. Obviously, I'm going to use the substitution. Cosine of phi is equal to u, negative sine of phi d phi is du, or sine of phi d phi, is negative du. So this becomes 2 pi over 3 times the integral. Be careful how the limit of integration is going to change. Cosine of 0 is 1, cosine of pi over 2 is 0, times negative du, and then that negative is going to flip right away. So 2 pi over 3 evaluated from 0 to 1, right? Because I'm going to flip it. And here I have 2u plus 2u squared plus u cubed. So 2u plus 2u squared plus u cubed du. And now this is a Cal 1 integral that you should know it. I made a mistake somewhere. This is not 2, this is 3, and this is 3. Sorry about that. Right? A plus b cubed is a cubed plus 3 times a squared b plus 3ab squared plus b cubed. So when I sorry about that. When I expanded this 1 plus cosine phi cubed, it's 1 cubed plus 3 times 1 squared times cosine plus 3 times 1 times cosine squared plus cosine cubed. Okay, now it's correct. So I have here 3 and here 3. And then just let's finish this problem. 2 pi over 3 times 2u over 2 plus 2u cubed over 3 plus u to power 4 over 4. Evaluated from 0 to 1, it's 2 pi over 3 times plug 1, you get 1 plus 2 over 3 plus 1 quarter minus 0 everywhere. And we are finally done, I hope. So here I have, again I made a mistake. Yes, so here I made a mistake. I forgot this, to change it to 3. And this one changes to 3. This doesn't stop, huh? So these are not canceled, So 3 over 2, 3 over 2, this is 3 over 2. 3 and 3 cancel, so I just get 1. So 3 over 2 plus 1 plus 1 quarter. And that's 2 pi over 3 times 4. Okay, 2 times 3 is 6 plus 4 plus 1. And that's 2 times 11 times pi over 4 times 3. Or finally, that's 11 pi over 6, because I cancel this and this. And we are done. Thank you very much, guys. Thank you very much for the semester. Good luck to all of you. I hope that this is the last semester at John Abbott to all of you. I hope you had a good time at John Abbott. Now way more interesting life expects you. Unfortunately, you're not going to experience the student life in September. All the universities are going online. The only positive thing here is that you have